just qualitatively. I hear exponential, right? And you can either have exponential increase or exponential decay. In this case, is it exponential growth or exponential decay? Decay, right? Because you have kappa, it's always positive, right? No, I haven't said that, but like it has to be always positive for a reason that is going to be immediately obvious. Because I have small k goes from 0 to infinity, right? So my 2 pi k squared can be as large as you want, I mean, in this series. So if kappa is negative, what actually happens? My solution is going to blow up as fast as you want, really. So if k actually has any component that is goes to infinity, I mean, if the decay of the Fourier series is not fast enough, my solution can blow up immediately if kappa is negative. So that's why also in reality, I don't think any of us have counted any physical equations that has a negative diffusion coefficient, right? Because the solution is actually going to blow up almost immediately. Okay. Well, unless you have any other stronger, even stronger terms to counter it. I mean, I actually have seen equations with a negative diffusion coefficient, but then you have a fourth order derivative term that is even stronger to counter it. So here we assume kappa is positive, and therefore we have exponential decay. And that's actually why when you were looking at the solution on the screen, the solution gets smoother and smoother because it gets decayed. Okay? And how about the rate of decay? What is the rate of decay for that A? 2 pi k squared times kappa, right? So first of all, there is a kappa, which means the larger the kappa is, the faster the decay is. That's why when we put a very strong diffusion coefficient, things get smooth very fast. And also, it's proportional to 2 pi k squared. That's a very interesting thing that cannot be neglected, which means the higher the k is, which means the smaller the period is, the faster the decay is. Okay? And can we see that this actually happens over here if you make, let's just make an experiment. I have a very fast oscillation here. Is this a big K or small k? It's big K. And let's have a small k. Okay, I'm going to release it, and which part of, is my left side of the screen going to decay faster, or right side of the screen is going to decay faster? Left, right. It's very obvious, right? So that's the effect of the diffusion equation. If you do Fourier analysis to it, you're going to see that the faster Fourier components is going to decay much faster. And I actually, when I draw it, I didn't draw it perfectly, right? So there are some residual low frequency oscillations on the left hand side that is decaying slowly, as you can see here. All right. So that's actually a very successful story of analytical methods for partial differential equations that actually can describe the behavior very well. But as you can imagine, as soon as we introduce some nonlinearity, for example, if I make kappa a function of W, then all the analytical methods are gone. You cannot do it anymore. The Fourier series, so basically my kappa would now depend on the summation of all the Fourier series, and I cannot do it anymore. And all these numerical methods we are going to be studying is going to be able to deal with it, right? So, for example, if you are looking at a heat equation, the diffusion of temperature, and if the diffusion coefficient is actually temperature dependent, which is actually the case in all the scenarios, analytical methods wouldn't be applicable anymore, and you have to go to numerical methods. Any questions? No? Okay.